Let's start by graphing the line x plus y is equal to 1. This one's easy enough to, I think, solve for y. So if we subtract x from both sides, we get that y is equal to negative x plus 1. This means that the y-intercept is at 0, 1, and the slope is negative 1, giving us a second point. Since there is a strictly less than inequality in this problem, I will use a dotted line, and let's graph that. This line now represents the barrier. I'm going to do a test point, which I think I'll use 0, 0 since it's not on the line. So I will test 0, 0, see what happens. And x plus y is less than 1. 0 goes in place of x and y. 0 is in fact less than 1. This is true. This means I shade below the line. So for this one, again, we want 3x minus y is equal to 2. I want to actually graph that as a solid line. If I add y to both sides, we get 3x is equal to 2 plus y, and then if we subtract 2, we get our equation y is equal to, I'll put 3x minus 2, just flip it around here. The y-intercept is at 0, negative 2. The slope is 3, or if we go over 1 and up 3, we get a second point, and I'll draw a solid line between these. This line represents the barrier. Again, I can use 0, 0, that's the most obvious choice. So I'll take my equation, or really my inequality, put 0 in place of x, 0 in place of y, and see if that, this is true. This simplifies to 0 is less than or equal to 2, and no, that is false. This means that I don't want to shade in the region that contains 0, 0, therefore I must shade down here. This is the answer, it's this shaded region. For this inequality, I need to consider the line negative 2x plus 4y is equal to 12. I think this one, I won't solve for y. I'll use an x and y intercept approach. So to get the x-intercept, that of course means y is equal to 0. My equation becomes negative 2x is equal to 12. The 0 in place of y makes that go away. Dividing both sides by negative 2 gives me my x value of negative 6. For the y-intercept, this, of course, means that x is equal to 0. My equation simplifies to 4y is equal to 12. When I divide by 4, obviously y is equal to 3. So my 2 points, x equals negative 6 means we're on the x-axis, and y equals 3 in this case means we're on the y-axis, the x and the y-intercepts, and I'm going to put a dashed line between those. There's the line. I again can use 0, 0 as a test point. So let's test the point 0, 0. So in my equation, that is negative 2x plus 4y greater than 12. 0 in place of both x and y is clearly going to make this a false statement. 0 is not greater than 12. Therefore, I want to shade above the line. So this is my answer. All right, so let's graph the line y is equal to negative x plus 7, but as a dashed line. This has a y-intercept of 7. The slope is negative 1, meaning I get the second point, and let's connect these. All right, so the test point, I guess I can use 0, 0 again, nothing wrong with that. Test 0, 0. That means I take y is less than negative x plus 7. 0 goes in place of y. It also goes in place of x. Is 0 less than 7 true? And of course the answer is yes. That means I want to shade below the line. So this is the region that makes the inequality true. Okay, we want to graph negative 3x minus 2y is equal to negative 6. So I'm using an x and a y-intercept approach. I think this is going to work out nicely. For the x-intercept, we're letting y equal 0. The equation becomes Negative 3x is equal to negative 6. Dividing both sides by negative 3 gives me x is equal to positive 2. And likewise, for the y-intercept, if x is equal to 0, the equation becomes negative 2y is equal to negative 6. Therefore, after dividing by negative 2, y is equal to 3. So let me plot those 2 points. So I plotted a solid line because there was an equal sign in the original problem. 3 went on the y-axis and 2 went on the x-axis. Again, I'm going to test the point 0, 0 in my original inequality. See if this is true. I can already see that after I plug in 0 for x and y, this is going to be a false statement. This is not true. Therefore, I want to shade above the line. All right, x is greater than or equal to y plus 5 means we need to graph a solid line for x equals y plus 5. So if you subtract 5 from both sides of this equation, you get x minus 5 is equal to y, which I like to write as y is equal to x minus 5. These are the same thing. The y-intercept has a y value of negative 5, and the slope is positive 1, so you go over 1 and up 1. I'll draw a solid line through these 2 points. We can again test 0, 0. That seems to be working for all of these. So for x is greater than or equal to y plus 5, 0 goes in place of x, 0 goes in place of y. We get 0 is greater than or equal to 5, which of course is false. And this means I don't want to shade at 0, 0 or anywhere up here. I'm shading below the line. Y plus 4 is less than 8. Let's look at, well, what if y plus 4 is equal to 8? If you subtract 4 from both sides, you get y is equal to 4. That is a horizontal line at 4, but it is a dashed line. This is my barrier. I'm going to test 0, 0. So that is in y plus 4 less than 8. If you put 0 in place of y, you get 4 is less than 8, which is true. So you do want to shade below the line, which is this region. One thing to point out here is that there were no x's in this statement. I knew I was going to get a horizontal line because of this, but also in your test point, this x equals 0 goes nowhere. This 0 went in place of y, and we still got to our final answer. For negative y is less than 2, let's see, we're graphing negative y is equal to 2 as a dashed line. If you divide both sides by negative 1, we get this is equivalent to y is equal to negative 2. That means at negative 2, there is this horizontal line. I will test 0, 0. Again, that x equals 0 goes nowhere. The only thing I have to do is put 0 in place of y. And, oh yeah, this is true. 0 is less than 2 is true. So I am shading this region here. We saw that y equaling a number was a horizontal line. So if x equals a number, that is a vertical line. This is the graph of just x is equal to 5. That is a vertical line at x equals 5, and it's a dashed line. I have my barrier. I have to choose either to the left of it or to the right of it, so that's really the only difference here. Instead of saying below, I have to say left or right. If I test 0, 0, this time x equals 0 is the only thing I have to consider because that y value of 0 is irrelevant. Is 0 greater than 5? And the answer is no. That's the point located right here. I don't want to use this point. I don't want to use anything over here. Therefore, I'm shading to the right of this graph, this stuff. For x is equal to negative 7, that is a vertical line at 7. Let's draw that. There I have a solid vertical line at x is equal to negative 7. And all right, we're testing 0, 0 one more time. For x is less than or equal to negative 7, 0 goes in place of x. Is that less than or equal to -7? The answer is no. So this time I'm not shading to the right. I'm shading to the left of this line, and those points represent the answer. Questions 11 through 16, I'll refer to the following function. F of x is equal to 2x squared minus x plus 1. Starting with 11, I want to evaluate f of 0. And again, all this means is wherever you see an x, put a 0. And I'm going to just be careful and use parentheses around every time I enter in a value. So I've done that first step, and the rest is just to simplify it. So let's see. 0 squared is just 0. Minus 0 I don't have to write, so I can put plus 1. 2 times 0 is 0, so f of 0 is equal to 1. Now let's make a note off to the side that what this symbol means is at x equals 0, we get y is equal to 1 back. So this symbol never changes. It's just a convenient way to say what does the function equal at x is 0, and over here is that value, y is equal to 1. For f of -2, this would be 2 times -2 squared minus -2 plus 1. So simplifying this, we get 2 times -2 squared is 4, a minus is a plus 2. So f of -2 is equal to 2 times 4, which is 8, plus 2 is 10, plus 1 is 11. In 13, we want f of 3. So f of 3 is equal to 2 times 3 squared minus 3 plus 1. This simplifies as 2 times 9 minus 3 plus 1. So that is 18 minus 3 plus 1. We will add and subtract moving left to right. So 18 minus 3 is 15 plus 1 is 16. F of 0.5, again just plugging this directly in, we get 2 times 0.5 squared minus 0.5 plus 1. So f of 0.5 is equal to, okay, 0.5 squared is 0.25. We're just simply subtracting 0.5 and then adding 1. So f of 0.5, okay, it's going to be 0.5 minus 0.5 plus 1. F of 0.5 is simply 1. To solve f of 1 minus 2, it is completely okay to rewrite this problem as f of -1. Simplify the 1 minus 2 and then plug that brand new number into the function. When we do this, that is 2 times -1 squared minus -1 plus 1. This is 2 times 1 plus 1 plus 1. That's 2 plus 1 is 3 plus 1 is 4. Okay, I want f of -5. This is 2 times -5 squared minus -5 plus 1. So f of -5 is, if we square a negative, it becomes a positive 25. In this case, the minus of minus is a plus 5, and then we get plus 1 at the end. F of -5 is 2 times 25, that's 50, plus 5 plus 1. Our final answer is f of -5 is equal to 56. And again, just to kind of like for finishing this portion of the homework, all this is saying is you're choosing -5 for x, and all the work we just did is telling you that the corresponding y value is 56. And also, the idea of a function is you put one number here and you get one number back here. We put one thing in place of x, we got one thing back for y. Questions 17 through 20 pertain to the function g of x equals 1 minus x over x cubed. So starting with 17, what is g of 1? I place a 1 into all the x's. I don't really have to be as careful with parentheses, but I put 1 in the denominator just to be a little bit careful. 1 minus 1 is 0. The denominator is 1 cubed, which is 1. The entire answer is just 0. It's completely fine to work across as I did, but I'll put it into one statement. G of 1 is 0. For 18, G of negative 1 is 1 minus a negative 1. I'll be careful with parentheses this time because there's a negative. The denominator I have negative 1 cubed. Let's see, a minus is 1 plus 1, and if I cube a negative, it stays negative. This is 2 divided by negative 1. My final answer is simply negative 2. Concisely, that's G of negative 1 is equal to negative 2. In 19, I'm going to choose to use a fraction, but you could do this problem with decimals since 1/2 is the same thing as 0.5. But this way, we have 1 minus a half divided by 1/2 cubed. The numerator is simple because 1 minus a half is simply a half. The denominator, if you cube a half, you're cubing 1, which is 1. You're cubing 2, which is 8. This is 1/8. And when you divide a fraction by a second fraction, you take the product of these two, provided that you flip this second fraction. So this is equivalent to, it's not really 1/2 divided by 1/8, instead it's 1/2 times 8 over 1. I know that 8 divided by 2 is 4, and that's my final answer. G of 1/2 is equal to 4. And lastly, G of negative 2/3. Same idea. We have 1 minus a negative 2/3, being careful with parentheses, divided by negative 2/3 cubed. Alright, in the numerator, it's a minus. This is really 1 plus 2/3. And the denominator is going to be negative because you're cubing a negative. If you cube 2, you get 8. And if you cube 3, 3 times 3 is 9 times 3 is 27. Now in the numerator, this 1 you could really think of as 3/3, which you're then adding 2/3 to. That's a total of 5/3. That's the sum of the numerator. It's 5/3. Your denominator is 8/27. You can make the whole thing negative by moving this negative to the front of the fraction. So a negative down here just means that your answer is going to be negative. So this thing looks like a mess, but G of negative 2/3 is simply negative 5/3, but I'm going to multiply by the reciprocal of the denominator, 27/8. 3 goes into itself once, it goes into 27 9 times. I can now simply multiply the numerators and the denominators to get my answer. It's negative 5 times 9 is 45, and the denominator is 8, so that's negative 45/8. I think I'll leave it just like that. For questions 21 through 24, this is kind of subjective depending on how many points that you choose to get your graph. So I'm just going to choose, I think, maybe 5 points for every single one, just so I get an idea of what the equation looks like. You might choose 5 different ones, so our answers may vary a little bit, but let's start with f of x is equal to 2x minus 3. I think I'll just, for this one, be pretty systematic and say, I'm going to evaluate f of negative 2, get its corresponding y value, and then graph it. We'll just see if it works. This means I put negative 2 in place of x and solve for y. So that's negative 4 plus 3. F of negative 2 is equal to negative 1. Again, this means negative 2 for x, negative 1 for y. Alright, so let's now choose negative 1. F of negative 1 is 2 times negative 1 plus 3. So f of negative 1 is equal to negative 2 plus 3. And when you simplify that, it just becomes positive 1. So we get the point negative 1 for x and 1 for y. About f of 0, that's 2 times 0 plus 3. So that's f of 0 is equal to 3. That one was easy. Now that I think about it, maybe even just 3 points is enough. I know this thing is a linear equation, so with these 3 points, I'm just going to draw the line that goes between them. This is what I think my equation looks like. It's a line containing the 3 points that I found. For g of x equals x squared minus 4, all right, let's start the same way. I'm going to try, I don't know, I think maybe -2 again. So g of -2 is -2 squared minus 4. If I square -2, it's going to be 4, and 4 minus 4 is 0. So g of -2 is 0. That's right here. -2 for x and 0 for y. All right, yeah, we'll try -1. G of -1 is -1 squared minus 4. That's 1 minus 4, and that's 3. G of -1 is 3. -3. It's here. The next one will be easy. G of 0, that's 0 squared minus 4. That's simply just -4. 0 for x, -4 for y. If I look at g of +1, that's going to be 1 squared minus 4, which is just, again, 1 minus 4, which is -3. I think I do see a pattern here. If I were to pick now +2, I think it's going to be at 0. If I put 2 here, I get 4, and 4 minus 4 is 0. I think I can see what this graph is doing. So it's going to be some type of equation that goes through these points. It's not a straight line, it's kind of curved a little bit. Let me sketch that up here. Not a perfect sketch, but that is going to be the general shape of the graph. You can choose some more points just to verify this for yourself. The function h of x is equal to the absolute value of x plus 2. So let's see, going with my standard points, -2 means I put -2 in place of x and add 2 to it. So h of -2 is, it's just 2 plus 2, which is 4. At -2, I get 4. At -1, I get the absolute value of -1 plus 2. Okay, that's just 1 plus 2. That's going to give me 3. At -1, I get 3. We'll try out h of 0. That's the absolute value of 0 plus 2, which that's easy. That's just 2. Maybe I'll again look at one more point. I think we're going to get a different trend here. It's not just going to be a line through those points. If I look at h of 1, the absolute value of 1 plus 2 is the same thing as just 1 plus 2, which is 3. That's this point right here. So the graph starts moving back up. So the entire equation is going to be this like V-shaped graph through those points. This is the graph of the absolute value of x plus 2. Last one here, k of x is equal to x minus 1 quantity cubed. I think I'm going to choose a different starting point here. I'm going to start at, I guess, maybe -1. That's -1 minus 1 cubed. That's -2 cubed. K of -1 is equal to -8. If I tried -2, I kind of saw ahead of time that the number is going to fall off the grid that I put down. This time at -1, I got a result of -8. So let's try 0. K of 0 is 0 minus 1 cubed. That's just -1 cubed. So k of 0 is simply -1. That's right here. I think the next one will be simple if I stick with this pattern. K of 1, what's that? That's 1 minus 1 cubed. That's simply 0 cubed. I don't even need the parentheses. K of 1 is equal to 0. Okay, we'll try, I guess, K of 2. That's going to be 2 minus 1 cubed. That's simply just 1 cubed, or said another way, K of 2 is equal to 1. Let's get one other point. I'm not really sure what the pattern is here. So I guess K of 3. That's 3 minus 1 cubed. That's 2 cubed. And 2 cubed is 8. So at 3, we get 8. I think I can kind of see the pattern now. This is kind of like your reference point, and if you go in this direction, the graph goes down 1, whereas if you go in this direction, the graph goes up 1. If I go over 2, I go down 8. If I go over 2, I go up 8. I think I know what this entire graph should at least somewhat resemble. This is my graph of K of x is equal to x minus 1 cubed. For 25, not a lot of equations to write out, it's simply getting our answer from the graph. Just a reminder, domain means all the x values, range means all the y values, and when we say something is a function, that means for anything in the domain, it corresponds to only one thing in the range. So let's check it out. To figure out the domain, you have to just look at these points. For this point here, it has a corresponding x value of -5. So you look to the x-axis to see the x value it corresponds to. This means -5 is in the domain. So let me record that. You get -5. Likewise, at -6, there's nothing, so -6 is not in the domain. So let's go to this point next. This has an x value of -4. This means -4 is in the domain. The x value here is -1. I get that too. This x value is 0. This x value is 2. And this x value is 3. That's it. Just looking at your points and recording what the x values are. Range is almost identical, except you don't look to the x-axis, you look to the y-axis. Instead of like working left to right, I'm going to work from bottom to top. So that means I encounter this point first. I'm not looking at the x value, I'm looking at the y value. And the y value is -2, so that's in my range. Moving to this point next, the y value is -1. Looking to this point next, the y value is 2. Looking at these 2 points, they both have a y value of 3. You could write it down twice, but there's really no point to do that. You can just say that 3 is in the range. It did refer to 2 points, but that's completely okay. This is my last spot. The y value is 5. And these are the numbers in my range. Now the question of whether this is a function or not is a matter of like looking at every point and seeing if there's another one above it or below it. And the answer is, well, not for this point, also not for this point. In fact, if you look at any of the remaining points, there's only one point with nothing above it or below it. So the answer to this question is yes, this is a function. For the remaining of these, I'm just going to kind of quickly go through them. You can refer back to question 25 if you want to see me more carefully go through every single point. But if I want to start with the domain, it's just all of the corresponding x values for these points. So we get -4, -3, -2, 0, 1, 2, and these both go to 3. So let me just write those down. -4, -3, -2, 0, 1, 2, and 3. Likewise, let's kind of quickly go through for the range. For the range, we have -2, 2, 3, 4, and 5. So that was -2, 2, 3, 4, and 5. Now, is this thing a function? So this idea of getting two y's for one x has to only go wrong once, and that happens at only one place on this graph. For this x value, this is at 3. This is in the domain of the function. So this is x equals 3. Notice that you get a point here. You get y is equal to -2, but you also get y is equal to 5. You have a point directly above the other. If this ever happens, even once, the answer is no. You do not have a function. It could happen multiple times, but as long as it happens once, not a function. For the domain, we get an x value of -4, -3, -1, 1, 2, and 3. So I'll jot those down. -4, -3, -1, 1, 2, and 3. And for the range, you only have one value. All these points appear at a y value of 2. 2 is the only number in the range. And is this a function? Yes. At each x, you only ever get one y above it. There's nothing else below it for every single point. For this graph, the only two x values in the domain are at -3 and at 2. So there's only two numbers, -3 and 2. The range is -3, -2, -1, 1, 2, and 3. And this is definitely not a function. Like over here, you have multiple points above and below the others. It happens twice, but whatever, it happened at least once, therefore not a function. The idea for these last four is quite simple. There's, again, not much to do except understand the vertical line test for functions. If you can find at least one vertical line that goes through the graph more than once, the graph is not a function. So for these four, I'll start with obviously 29. Clearly there's a lot of options here. There's many vertical lines that you could draw that go through the graph. So I'll put one right here. Here's a vertical line, and it goes through the graph, as a matter of fact, twice. And because that happened, this means it's not a function. So I'll just put not a function, or just no. Whereas if you look at question 30, no matter what vertical line you draw, no matter where you draw a vertical line, the vertical line only goes through the graph one time. So the answer to this one is yes. Yes, this is a function. For question 31, let's see, I just need one vertical line that goes through the graph more than once, and I'll choose this one right here. Maybe this was supposed to be at -1/2, but whatever the case may be, the answer is no. Whereas over in this one, this graph really didn't come out too great the way it was scaled. Like, this thing is supposed to be continuing forever in this direction. It never becomes vertical, even though it looks like really steep. And because of this, any vertical line that you draw is only ever going to go through the graph once. It kind of looks like it might match up here, but it's not ever vertical. So the answer to this one is yes, this is a function.